So in Chapter 7, we're going to talk about two words that are extremely important, association and correlation. Previously, correlation was, you were taught, it refers to the relationship between two variables. Now, let's discuss it in this context here. Instead of using the word correlation, we're going to talk about association. Association, as you may have known if you read the chapter, describes the relationship between two variables, two quantitative variables. Now, association, and here's an association of hurricanes. Now, over time. So, association has a number of characteristics. It can be positive or negative. It can be weak, moderate, or strong, or non-existent. And it can be straight or curved. So it's extremely important whenever you talk about association, you remember these three categories: positive or negative, it's strength, direction, strength, and linearity. Is it linear or not? Let's go to the next page. Okay, so we're going to look at some scatter plots. And so here's some examples. Here's positive, here's negative, here's curved. Here's another one that's curved. It goes up and then it goes down. Okay, in general, the only ones we're interested in are the ones that are straight or that we can make straight. Here's one that's random. Here's another one that's positive. So let's now the variables that we talk about when we're talking about a scatter plot. We have two variables that we talk about. I want to go back a page. Okay, we have the explanatory variable, that's the x coordinate, and we have the response variable, that's the y coordinate. Now, we've also talked about these in the past as stimulus and response, or x and y, and so on. But in this course, and in general, they'll be referred to as explanatory and response. And when we talk about the relationship between them, we would say the response variable versus the explanatory variable. So we're going to use that language a lot. Explanatory, the response variable versus explanatory variable. So let's go to problem 34. And let's go to the book. And so let's find 34. You can just do this in your notes, but we will do it together. So here's 34. Now, here's the idea in 34. Marijuana is considered to be an explanatory variable that explains, that is some kind of association with percentage of people that use other drugs. So in the countries that are listed here, we're looking for an association between percentage of people who use marijuana and percentage of people that use other drugs. Okay, so this will be a chance to go through the calculator and learn how to do this. I'm going to set my calculator to its default mode. Alright, so we're going to go to Stat and then Edit, and you're going to put in the numbers. So you can just skip ahead or whatever, you get the numbers in. Put mine in using the keyboard. And I'm going to double check. 34, 53, 7, 6, 23, 19, 37, 5, 40, 17, and 22. Okay, now let's put in the response variable, the other drugs. 3, 2, 1, 1, 16, 8, 14, 3, 3. Okay. Columns are the same length. Let me see if the numbers are right. 24, 31, 3, 3, 14, 8, 16, 1, 21, 3, 4. Okay. So I'll go to second and y equals, and then in the first plot I'm going to hit enter, and enter again. Notice that my type is the first type that's here. This is for the scatter plot. The next plot this is for the time plot. This is histogram. This is box and whisker plot that we use. This is box and whisker we don't use. And this is the normal probability plot. So anyway, we want to use the scatter plot. So I'm going to hit enter. Now it defaults to L1 and L2. If your lists are not in L1 and L2, then change these lists to be L1 and L2. Now I'm going to hit zoom in 9, and there's my scatter plot. Now I'm going to take a picture of this so we can, let me get rid of all these pictures. Okay, now I'll take a picture. Okay, now let's describe the association. The association is linear. It is fairly strong, and it is positive. There do not appear to be egregious outliers. Now, what is an outlier? There's two kinds of outliers. Here's a point that's sort of separated from the rest of the data on the x-axis. So here we have most of our data, and then we have a kind of a gap in the x-axis, gaps we associate with outliers, and then we have this data point. Now, is this an outlier? Well, yes and no. The thing is, it follows the trend line of the rest of the data, so it's not an outlier that we worry about too much. Okay, so that's one kind of an outlier. An ordered pair whose x-coordinate separates it from the rest of the pack. Now, if this ordered pair was down here or up higher, then we would be worried about it, because then it would be apart from the trend line, and it would affect the trend line heavily. Now, what's the other kind of outlier? That's an outlier whose x-coordinate is normal, but whose y-coordinate is abnormal, whose y-coordinate is above or below the rest of the pack around it. Now, that kind of outlier can affect the correlation, and I'll talk about how it affects correlation in a minute, but it doesn't affect the slope of the line very much, and that's the thing we're most concerned about. All right, so we've described the association. Now, I've mentioned correlation. Let's talk about correlation for a minute. What is correlation? Correlation measures the strength of a linear association. This correlation measures the strength of a linear association. Now, this is in the book. So, correlation has preconditions, of which I just mentioned one. First of all, the data must be quantitative. All right. Well, we know this is quantitative data. Okay. And then here's the next condition. The data must be linear. The scatter plot here. Scatter plot must be linear. Okay, and third condition, no outliers. Any of these conditions, data is not quantitative, scatter plot's not linear, or there's some really noticeable outliers. will preempt you from using correlation. In other words, you cannot use correlation unless your data is quantitative, linear, and does not have outliers. If there are outliers, that's the one condition you can work around. You make note of them, and you would compute the correlation with and without the outliers. Okay, so correlation measures the strength. So how does it work? Correlation, which is symbolized by the letter r, lowercase r, equals the sum of the z-scores of the ordered pairs, of the product of the z-scores of the ordered pairs. So you take each ordered pair, you calculate the z-score for the x-coordinate and the y-coordinate, you multiply them, you add all those products together, and divide by n minus 1, and you have the correlation. Now, correlation has properties. First of all, it goes from r is greater than or equal to -1, less than or equal to 1, always. Okay? R has no units. R is symmetrical. That is, if you do x versus y, the correlation for x versus y equals the correlation for y versus x. You can reverse the variables. The correlation's the same. That's because the correlation is made up of the sum of the products. A times b equals b times a. So it's symmetrical. R is not affected by sliding or scaling. Why? Because it's made out of z-scores, and z-scores are unaffected by sliding or scaling. As I said before, it measures strength of a linear association and no other kind of association. Okay? And it is sensitive to outliers of both kind. Both kind of outliers affect the strength of R. Okay. How do you calculate it? You're going to go through this. You're going to calculate the z-scores and do all of that? No. As you've known before, your calculator does all the work. So we get the calculator out. Now we already have the x-coordinates and y-coordinates. So we are going to calculate the line of best fit, and that will calculate correlation for us. But the first thing you're going to do is you're going to hit the second key, and then you're going to hit the 0 key, and that activates, it puts you in the catalog. The catalog, you're going to arrow down to diagnostic on. Oh, looked it too far. Diagnostic on, hit enter, and then enter again. You must turn the diagnostic on in order to see the correlation. Now we're going to hit stat, calc, 8, linreg. It defaults to L1 and L2. If you are using anything other than L1 and L2, then you must put them in. So I hit enter. Okay, so here's what I got. Correlation is 0.93. That's quite strong. Now, what do these other letters mean? A. A is the y-intercept. What this means is that if nobody in your country smokes marijuana, then the percentage of people that use other drugs is -3%. Now, how could that be? Well, let's look at the problem. Okay. The domain of the problem, in other words, the first x-coordinate that we get is 5, and it goes up to, 53 or whatever, Scotland. So 0 is not in the domain. Now, A is what y equals, what the consequential variable equals when the explanatory variable is 0. So often, when your domain does not actually include 0, then you're going to get a meaningless answer for what the consequential variable equals when the explanatory variable is 0. Okay, just so you know. Now, what is B? B is the slope. It's the rate of change. Now, what does B mean? In the context of the problem, B means that for every increase of marijuana, of 1% of marijuana users, the percent of people that use other drugs goes up by 0.615%. Okay, so let me say that again. For every increase, this is what B means. The meaning of B is for every increase of 1%. You got to put it in the units and contextualize it. For every increase of 1% of marijuana users, the percent of people in the country that use other drugs increases by 0.615%. Okay, so now here's the last question. Do these results confirm that marijuana is a gateway drug? That is, does marijuana use lead to the use of other drugs? And this ties into a very important idea, which is that correlation does not equal causation. Never, 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 at least in this course, never, never. Correlation never means causation. What does correlation mean? It is the strength of the association. That's it. Of the linear association. In this case, between percent of marijuana users and percent of other drug users. Now that strength has to be quite high. It doesn't mean cause and effect. There could be what we call lurking variables. A lurking variable affects both cause and effect. What would be a lurking variable that would cause the percentage of people to increase marijuana and use other drugs? It could be socioeconomic status of the entire country, either rich or poor. There's other factors, but the idea of lurking variables that affect both the explanatory variable and the consequential variable is very, very important. There's another kind of variable called the confounding variable, which only affects the consequential variable. So you want to remember this: confounding variables only affect the consequential variable. Lurking variables affect both. Now, how do you factor out compounding and lurking variables? By random controlled trials, by a controlled experiment. Subjects selected randomly and assigned to treatments randomly. Now, clearly, we cannot do a random controlled trial, an RCT, with drug users. It's illegal. It's inhuman. So, at this point, the only thing these statisticians can do is just point to correlation. Okay, so that's it for that problem. Now, in terms of the rest of the ideas for this chapter, there's one other thing, couple of other things I want to talk about before I just set you loose on the homework. And we'll do a little bit of the homework. Let's look at some of the homework right now. Let's go back. Oops, no, I don't want to go there. Why did I go there? I want to go here. Okay. Now I'm going to turn that off. Let's go to problems. Some of the problems at the beginning of the homework. Okay. And then we'll work on some of these. Let's do some of these together. Okay, problem 2. Suppose you collect data on each pair of variables. You want to make a scatter plot. Which variable would you use as the explanatory variable, and which is the response variable? Why? What would you expect to see in the scatter plot? T-shirts at a store, price for each number sold. Well, clearly this would be the explanatory variable would be price, and the consequential variable would be number sold. Lower the price, the more you sell, you would think. But usually these things aren't linear. What would you expect to see in the scatter plot? It might be linear, might not. You know, if you make it too low, some people stop buying them. They won't people, and you get too high. But it could have a curve that was, you know, not necessarily straight. Okay, but you feel like the association would be fairly strong. Okay, scuba diving, depth and water pressure. Now, depth and water pressure, well, it seems like depth is an explanatory variable for water pressure. But water pressure and depth kind of have a one-to-one correspondence to each other. Depth and I would expect depth and water pressure. I don't know if that's linear or not. I think depth and visibility is nonlinear, but I'm not sure. You can look those up in your science department. D, all elementary school students weight and score on a reading test. Okay, we would assume there's no correlation whatsoever between score and... Now, again, weight would probably be the explanatory variable, and score would be the consequential variable. But I would not expect there to be any relationship, so the scatter plot would look like this. It would look random. Now let's look at 3, climbing mountains, altitude, and temperature. The explanatory variable would be altitude, temperature would be consequential, and it would be negative and linear and strong, I would assume. Okay, for each week, ice cream cone sales, air conditioner sales. Neither of these cause each other. They could be either, because they have a lurking variable, which is heat. For people, age and grip strength, this would be linear, strong, and negative. Drivers, blood alcohol level and reaction time. Blood alcohol level is the explanatory, reaction time is the consequential, and it would be linear, negative, and I'm sure rather strong. Okay. Now let's go back to the book, and let's talk about a couple of ideas here. We talked about correlation, making a scatter plot. The conditions for correlation, looking at association, we've done that. All right. The properties of correlation. Correlation, we talked about that. Correlation tables is kind of an interesting idea. You can make a table of a whole bunch of categorical, of quantitative variables, and then make a table that shows the correlation between all of them, and then look for where the correlation is the strongest between which pair of variables. This is something maybe we'll get into after you take the AP exam. And finally, re-expression. Straightening a curve. Now, what are we talking about here? Well, this is actually a homework problem. So let's go back to the book, to the homework, and turn that off. Turn that. Okay. This is near the end. Oh, too far. Chapter 8. Okay, planets. Let's look at this planets problem here. Okay. Now, for a bunch of reasons that I'm not going to go into right now, mostly because of correlation and what correlation allows us to do. Statisticians, by and large, whenever possible, like to deal with linear regression. So if statisticians have data that does not fit a linear pattern, statisticians will manipulate the data, re-express it in order to try to make it straight. Now the reason for that is it's just a lot easier to analyze. So let's do a scatter plot for 41. So get my calculator here, and I'm going to stat, edit. I'm going to clear out these two columns. Now, since I haven't done anything I haven't reset the calculator recently, so the diagnostic is still turned on. So 1, 2. Double check my entries: 2796, 1784, 887, 67, and 36. Okay. Now, I'm going to look at this, and I got 1 through 9. Alright, so let's do a scatter plot. So do second y equals. And I got L1 and L2, and I got the scatter plot turned on. So I just have to do a zoom 9 because I've changed my data. The data's so different. Okay, now you can see this is definitely not straight. It's exponential. Okay, so we couldn't use this to talk about correlation. So here's the described association. It's strong, it's nonlinear, and it's positive. Okay, and I would say there are no outliers whatsoever. So it's strong, nonlinear, positive, no outliers. All of those are important things to note. Okay, now, what are we going to do if we want to do linear regression? We want to talk about the correlation. What are we going to do? Well, it says, so we can't use correlation because it's not linear. So it says make a scatter plot showing the logarithm of distance versus position. Okay, so we're going to go to stat and enter, and we're going to go to L3 and go to the top, and we're going to type log and then second 2 and hit enter. Now, what do we have in L3? Let me put this over here for a minute. What is going on? Logs are exponents. So we have in L3 are the exponents needed to raise 10 to are the exponents of 10 that equals 36. So if I take 10 to the 1.5563, it equals 63. Now let's just test that. Okay. Let me clear this. So 10 raised to the power of 1.5563 equals, well, pretty close to 36. About as close as you can get. I need a few more decimal places. All right, so logs really are just exponents. So instead of trying to find correlation between the planet order and its distance from the sun in millions of miles, we're going to find a correlation between planet order and the log of its distance from the sun. But first, let's look at the scatter plot of L1 and L3. So I'm going to hit enter, so that I'm going to go here, and for the Y list, I'm not going to use L2 anymore. I'm going to use L3. And I'll hit zoom 9. Now, it's got a little wiggle to it, but it's fairly straight. it's definitely strong. So like we can call it strong, linear, and strong and linear and positive. Okay. So there's some limits to doing this though. So we could find the correlation. So let's do that. So I'm going to hit second and get out of here, clear this, stat calc 8, and I'm going to specify L1, comma, L3. So if I'm not defaulting to L1 and L2, then I have to specify the two lists that I'm using, even if one of them is L1. Okay, now that is really high correlation, so the strength of a linear relationship is really high. And here is the line of best fit, A and B. So now, this is planet position. This is the log of distance from the sun versus planet position, okay, in millions of miles. Okay, so A is the log of the distance from the sun when the planet number is 0. Okay, well, we don't have a planet 0. Okay. And B states that for each increase in planet position by one planet, the log of the distance from the sun, base 10, in millions of miles, increases by 0.27. And let's round that, 0.271. Why? Because logs represent a lot of quantity. All right. So we've said what A and B is and what R is and everything. And so that's what we do with re-expression, and that's what that's all about. And that's pretty much it for Chapter 7. So start on the problems. Do as many of them as you can. If you have any questions about anything, let me know or bring them up in class. If you're finished with this, then start working with somebody on the homework problems.